In this lesson, we will discuss the continuous extension of a function to a point. Consider this function y equals sine of x over x. This function is continuous at every point except for at x equals 0, at which point it has a removable discontinuity. So since this function has a removable discontinuity, it's possible to define a new function that kind of fills in this little hole, but it also equals the sine of x over x for every other point. So this function will be called the continuous extension of the function sine of x over x to the point 0. We see that from this graph that the limit as x approaches 0 of sine of x over x equals 1. Is the limit from the left-hand side and the right-hand side of sine of x over x equals 1. So we could define a continuous extension of this function by defining the function to equal 1 when x is 0. This would kind of fill in this little hole and therefore remove the discontinuity. So let's define the function capital F of x. So capital F of x will equal sine of x over x for every value of x other than 0. And then to fill in this hole, we're going to define capital F of x to be 1 when x is 0. So the graph of capital F of x would look like this. So it would be a continuous function everywhere. Now we've removed the discontinuity. This capital F is called the continuous extension of sine of x over x to the point x equals 0. So in general, this is how we can define a continuous extension when you have a removable discontinuity. So suppose f has a removable discontinuity at x equals c. So we know that means the graph just has a little hole at the point x equals c. And therefore, the limit of f as x approaches c will exist. So let's say the limit of f of x as x approaches c equals some number L. Okay, so the graph is continuous, but it has a little hole, and the hole has coordinates c comma L. We can fill in this little hole. In other words, we can remove the discontinuity by defining a new function called capital F of x, such that capital F of x equals little f of x everywhere f is defined, and then you define capital F of c to be equal to L. So therefore, the function capital F will be continuous at c, and we call this the continuous extension of f to x equals c. So by doing this, we can remove removable discontinuities. Let's see an example. Consider the function f of x equals x squared plus x minus 6 over x squared minus 4. This function has a continuous extension to the point x equals 2. This function can be factored. The numerator factors as x plus 3 times x minus 2. The denominator is the difference of squares, so this factors as x plus 2 times x minus 2. And so this function has a common factor of x minus 2 in the numerator and denominator. This function has discontinuities at x equals 2 and at x equals minus 2. But since the numerator and denominator both have a common factor of x minus 2, the discontinuity at x equals 2 is a removable discontinuity. So in order to define the continuous extension at x equals 2, we need to find the limit of f of x as x approaches 2. So I'm going to use the factored form. So in the limit of f of x as x approaches 2, I can cancel the common factor of x minus 2 because we're not considering what's happening at x equals 2, just what's happening as x approaches 2. So I can cancel these common factors. This equals the limit of x plus 3 over x plus 2. This is a rational function, and we won't be dividing by 0 if we plug in 2 for x. So by direct substitution, I can evaluate this limit. This will equal 2 plus 3 divided by 2 plus 2, which simplifies to 5/4. So this function f has a removable discontinuity at x equals 2. The point that's missing on the function has coordinates 2, 5/4. So if we can define a new function that fills in this hole, then we will have found the continuous extension to x equals 2. So let's define the function capital F in the following way. So capital F of x will equal x squared plus x minus 6 over x squared minus 4 when x is not equal to 2. And when x equals 2, we will define capital F of x to equal 5/4. Now capital F of x will be continuous at x equals 2. So therefore this is the continuous extension of little f to the point x equals 2.